I want you to close your eyes for a second. Imagine you are shrinking down.
Yeah.
Smaller than a fingernail, smaller than, I don't know, a microchip. You're shrinking all the way down until you are standing right on the surface of a printed circuit board. Maybe the one inside your own phone.
It's a very strange landscape down there.
It is. You've got these copper canyons, towering black monoliths of silicon.
Mm-hmm.
But I want you to look at the invisible part. If you could put on a pair of special glasses, let's call them Maxwell goggles, and actually see the energy pulsing through that board, what would it look like?
Ideally, I mean, in a perfect world, it should look like a tightly choreographed ballet.
A ballet.
Yeah. Ribbons of light flowing smoothly, contained, disciplined, everything moving perfectly in sync.
But for a lot of designs, and maybe even the one you're working on right now, if you put those goggles on, it wouldn't look like a ballet.
Oh, no, not at all. It would look like a chaotic storm.
A storm. Lightning striking where it shouldn't, this fog rolling into areas that need to be clear, energy leaking out like water from a burst pipe.
And that storm is exactly why devices fail. It's why they glitch, it's why they reset randomly, and it's why, when you take them to the test lab, you fail your EMC compliance test.
That is the absolute worst feeling in the world.
It's skull-crushing.
You've built the thing, it works perfectly on your desk, and then you put it in the chamber and it lights up the spectrum analyzer like a Christmas tree.
And usually the engineer is standing there just scratching their head because, looking at the schematic, everything is connected perfectly. Pin A goes to pin B.
Mm-hmm.
The logic is totally sound.
But the physics. The physics is broken, and today we are going to fix that. We are going to break a fundamental habit that I guarantee probably 90% of our listeners still have. We are going to take the standard electricity is like water flowing through pipes analogy.
Oh, yes, the old class.
And we're going to throw it right out the window, flush it. Because when it comes to high-speed PCB design and electromagnetic compatibility, or EMC, that analogy isn't just imperfect, it's actually dangerous.
It's so dangerous. It creates this false sense of security. It makes you focus on the copper, on the pipe, when you should be focusing on the space around the pipe.
Welcome to the Deep Dive. Specifically, this is episode 4 of the EMI Control Podcast. Today, we aren't just talking about connecting dots on a schematic. We are getting serious about layout.
Yeah, this is where the rubber meets the road. Or, I guess more accurately, where the field meets the dielectric.
I love that. Now, before we really jump in, we need to acknowledge the source of this deep dive. We are partnering with Fraisu Electronics for this. All of the insights, the diagrams we're describing, and the core philosophy. It all comes directly from the EMC EMI design course led by Dario Fraisu.
And Dario is a true heavyweight in this industry. He's a CEO, a principal engineer, and a specialist who has spent, years debugging designs that should have worked, but they didn't. His approach is so refreshing because he strips away all the black magic and just reveals the physics underneath.
And his mission for us today is pretty clear. We are moving beyond basic circuit theory. We are stepping into the realm of Maxwell's equations. Now, listener, I can feel you tensing up. Do not panic. We are not doing calculus. I barely survived calculus too.
No math today, I promise.
Yeah.
Maxwell's equations are usually taught as these terrifying differential equations you have to solve on a chalkboard. But Dario's approach is totally different. We're going to use Maxwell's work as a visualization tool. We want to help you see that invisible geometry we were talking about.
So we can design boards that don't just function, but are actually robust.
Exactly. We're chasing what I like to call the holy trinity of EMC.
Right.
First, reliability. The device works every single time, not just when the moon is full. Second, immunity. If I turn on a vacuum cleaner next to it, it doesn't crash. And third, compatibility. Your device doesn't destroy the Wi-Fi signal for the entire building.
Okay, so let's start there. Let's unpack this water analogy problem. I feel like that analogy is the first thing we all learn in Physics 101. Voltage is pressure, current is flow, the wire is the pipe. It's intuitive. So why does it fail us so badly when we get to PCB design?
It fails because it focuses, 100% of your attention on the conductor, on the wire. In the water analogy, if the pipe isn't leaking, you're fine, right?
Right.
The water stays in the pipe. The space outside the pipe is completely irrelevant. You can run that pipe through a swimming pool or through a vacuum, and the water flowing inside just doesn't care.
Okay, so the copper traces the pipe. As long as the copper is continuous, the signal gets there. That's the mindset.
That's the mindset. And it's true for DC, maybe. But in high-speed electronics, and we'll define what high-speed really means in a bit, the energy isn't just in the trace. The signal travels as an electromagnetic field in the space between the conductor and its reference.
Wait, hold on a second. You're saying the energy isn't in the wire? I paid a lot of money for those copper traces on my board.
Yeah.
You're telling me they're irrelevant?
They aren't irrelevant. They're absolutely critical.
Yeah.
But they are the guide rails.
Mm-hmm.
But the train, the actual energy moving from the driver to the receiver, it rides on the fields between the rails.
Yeah.
The energy is in the dielectric. It's in the fiberglass and epoxy of the PCB material itself.
So the energy is actually in the sandwich, not just in the bread.
That is a surprisingly accurate analogy. It really is.
Yeah.
Let's visualize a cross-section of a simple double-layer PCB to make this really concrete. So you've got your top layer, let's color that red, that's your signal trace.
Okay.
Then you've got your bottom layer, we'll color that blue. That's going to be your reference plane.
And in between them is the PCB material, the FR4, the filling of the sandwich.
Exactly, the filling. Now imagine a signal pulse traveling down that red trace. What is actually happening? It isn't just a bunch of electrons bumping into each other like marbles in a tube. You have to visualize two invisible forces expanding out from that conductor. First, you have electric fields.
Right, and in the diagrams from Dario's course, these are shown as black arrows.
Yes, these black arrows shoot out from the signal trace. And here is the absolute key. They are looking for a place to terminate. They are actively searching for a difference in potential.
They're searching for a landing strip.
A landing strip, that's a perfect way to put it. And simultaneously, you have magnetic fields, which are shown as blue circles, and they wrap around that trace like a tunnel or a sleeve.
Okay, so we have black arrows shooting out and blue circles wrapping around. This is that invisible geometry you mentioned.
It is. And here is where the layout engineer becomes the director of that ballet we talked about. The behavior of those black arrows, the electric fields, depends entirely on where that blue reference plane is. If the reference plane is right underneath the signal trace, nice and close, those electric fields are magnetically drawn to it. They shoot down, they hit the plane, and they terminate.
So they're contained, they stay inside the sandwich?
Precisely. They are tightly coupled. The energy is focused in that dielectric space between the trace and the plane. It's disciplined. It flows exactly where you want it to flow.
Okay, now let's flip that. Let's look at the horror movie version. What is the no-plane nightmare?
The nightmare is you remove that blue layer from underneath. Maybe you just, I don't know, forgot to pour the copper, or maybe you routed your trace over a gap in the plane because you're being lazy. Now, those black arrows, the electric fields, they shoot out from the trace, but there's nothing immediately below to catch them.
They just keep going.
They flare out, they expand into the world, searching for any reference they can find. Maybe they latch onto a metal chassis. Maybe they hit a completely different sensitive analog circuit nearby. Or maybe they just radiate out into space as radio waves.
That sounds like total chaos.
It is chaos. And this is literally what happens when you fail an EMC test. When you go to a test lab for the radiated emissions test, they put an antenna a few meters away from your board. They are measuring how much that field energy has escaped. If you don't provide a reference plane close to your signal to catch those fields, they will escape, and that antenna will hear them.
So the quickest way to fail is to just let your traces float around without a solid reference nearby.
It basically guarantees failure. And it works both ways, too. If your fields are flaring out, your trace is essentially a big antenna just waiting to pick up garbage from the environment. So your device becomes sensitive to noise, too. It's a double whammy.
I want to pause on a specific term you keep using, and I notice you're very careful about it. You keep calling it the return reference plane. You haven't said the word ground once. Is that intentional?
Very intentional. This is a massive pet peeve of Dario's, and frankly, it drives most EMC specialists completely crazy. The word ground is a dirty word in layout design because it's just so vague.
But we use it all the time, right? Connect this to ground. Where's the ground pin?
I know. But think about the water analogy again. In that model, ground implies a drain, like a magical sink where the water just disappears into the earth and you never have to worry about it again.
Right. It just goes away.
But on a PCB, nothing goes away. The electrons on your board, they don't know where the dirt outside your house is. They only know where they came from, the battery or the voltage regulator. They want to go home, not to the earth.
So that big copper pore isn't a drain?
No, not at all. It has two very active, very critical jobs. First, as we just discussed, it provides the reference potential for the electric fields. It's the landing strip that catches the arrows. But second, and just as important, it is the return path for the current.
The circle in circuit. The current has to come back.
Exactly. You cannot have a circuit without a return path. It's a fundamental law. If 10 milliamps of current goes out the signal trace, 10 milliamps must return to the source. And where does it flow? It flows through that plane. Calling it ground makes you think it's just this static 0-volt pool. Calling it a return reference plane reminds you that it is an active highway for return current.
I really like that distinction. It forces you to respect that layer. It's not just leftover copper, it's literally half of your circuit.
It is the hero of the board. And if you treat it like dirt, your board will treat you like dirt.
Okay, so let's talk about that return journey. You mentioned the current has to get back. This brings us to one of the most common mistakes I see in multi-layer boards, the stack-up strategy.
This is where things get really tricky and where a lot of projects get into trouble before a single trace is even routed. Let's say you have a 4-layer board. You have your signal on layer 1, the top. You have your reference plane on layer 4, the bottom. We decide, hey, I need to distribute 3.3 volts to all my chips, so I'll put a power plane on layer 2.
That seems logical. I need power, I need ground. Sandwich them in the middle to make a nice power distribution network.
It seems logical, but remember the physics. Ideally, you want the return reference plane immediately adjacent to your signal trace. But in this scenario, you have signal on layer 1, then power on layer 2, then your reference way down on layer 4. The power plane is now the closest piece of copper to your signal.
So the electric fields, those black arrows, they're going to be attracted to the power plane.
Physics doesn't care about your schematic names. It doesn't care that you called one plane GND and another plus 3V3. Physics seeks the path of least impedance. If the power plane is closer, the fields will terminate there. The return current wants to flow on that power plane because it is physically adjacent.
But wait a minute, the power plane is at 3.3 volts. The reference plane where the source is grounded, that's at 0 volts. They aren't connected to each other. So how does the current get back to the source if it's riding on the power plane?
That is the power plane dilemma. You have just stranded your return current on a voltage island. It is flowing happily on the 3.3 V plane, but it needs to get to the 0 V plane to complete the loop. But there's no wire connecting them.
And if you did connect them with a wire, you'd create a dead short and, burn your board up.
Exactly. So the current is trapped. How does it get home?
You're going to tell me, I hope.
It has to jump.
Jump? Like through the air? What do you mean jump?
Through the dielectric between the planes. It uses something we call displacement current.
Okay, let's slow down here. Displacement current. That sounds like something out of science fiction. What is actually happening?
Think about a capacitor. You have 2 metal plates separated by an insulator. Current can't flow through the insulator, right? It's a physical barrier.
Yeah.
But if you apply a changing voltage, an AC signal energy is transferred across that gap. The electric field changes, and that changing field acts like a current.
Ah, okay. So the power plane and the ground plane, they act like the 2 plates of a giant board-sized capacitor.
Yes, that's exactly what they are. The high-frequency energy effectively jumps through the gap between the planes using this capacitance.
Huh.
But here's the problem. Jumping is hard work.
It's not a free ride.
No, not at all. It introduces significant impedance. It's not a smooth highway anymore. It's an obstacle course. The electrons are struggling to push that field energy across the dielectric, and that impedance creates a voltage drop across the planes.
And a voltage drop on a reference structure
This
is...
is noise. We call it ground bounce
Yeah.
or a rail collapse. Basically, because you forced the return current to do parkour between layers to get home, you've just generated a massive amount of noise that ripples through your entire power distribution network.
So just by choosing the wrong stack up, by putting that power plane between the signal and its reference, we broke the EMC performance of the board.
You broke it before you even routed a single trace. The golden rule, according to Dario Fresso, is simple. The best design places the return reference plane directly adjacent to the signal trace. Don't make the fields jump if you don't have to.
But sometimes we have to move signals around. We run out of room on the top layer, so we have to dive down to the bottom layer using a via. What about that?
Vias are a necessary evil, but they are treacherous if you don't think about the fields. Let's visualize a signal trace on the top layer, layer 1. It's happy. It has a nice, solid reference plane right underneath it on layer 2. The fields are contained.
Life is good, but now we drill a hole. A signal via the trace dives all the way down to layer 4.
Okay, so now the signal is on layer 4. For the fields to be happy, its reference needs to be on layer 3, right above it.
Right, same principle.
So if you have a symmetrical stack-up where layer 2 and layer 3 are both return reference planes at the same voltage, let's say they are both G and D, then this is what we call easy mode.
Okay, why is that easy?
Because you can put a stitching via right next to your signal via. A stitching via is just a little plated hole that connects layer 2 G and D to layer 3 G and D. It's a metal elevator for the return current.
Oh, I see. So the signal goes down its own elevator, and the return current hops onto the stitching via right next to it and rides down too. They stay together like buddies.
Exactly. The loop stays tight. The buddies travel together. But now, let's look at hard mode.
I have a feeling hard mode involves those different voltages again.
It does. Let's say layer 2 is G&D, but layer 3 is power.
Ah. Okay, so I can't drill a stitching I can't connect G&D to power with a metal tube.
Correct. That's a short circuit, smoke, bad day.
So the signal dives down to layer 4, but its return current, which was happily flowing on layer 2, gets to the via, and it looks down, and it sees nothing. There's no copper path for it to get to the new reference plane on layer 3.
So the return current is stranded on the top reference plane.
It is completely stranded. It has to fight its way through that interplane impedance, again using displacement current, to get to the new reference plane. This creates massive field spreading right at the via. I've seen engineers try to fix this. They say, oh, it's fine, I'll just put a decoupling capacitor right next to the via. And their logic is that the capacitor connects power to ground for AC signals, so it acts like a little bridge.
And Dario calls this the capacitor fallacy.
Why? It sounds pretty reasonable on the surface. A capacitor passes AC, right?
It passes some AC. But think about the physical construction of a capacitor. It has leads, it has internal structure, it has mounting pads on the board. All of that adds up to something called parasitic inductance, or ESL.
And inductance is basically resistance to a change in current flow.
Right. Think of a capacitor like a water tank. At low speeds, you can fill it and drain it easily. It acts like a buffer. But at high speeds, like the incredibly sharp edge of a modern digital signal, the pipes leading to that tank are too narrow. The water can't get in and out fast enough. The inductance prevents the current from flowing instantly.
So the capacitor stops looking like a bridge, and it starts looking more like a ball.
Exactly. As the frequency goes up, the impedance of that capacitor goes up. It becomes a wall. So the high-frequency return current arrives at the capacitor, sees this high impedance blockage, and says, nope, not going that way. It goes off searching for a different path, usually a much, much longer one, creating a huge loop antenna in the process.
So relying on capacitors to stitch your return paths it's a gamble.
It's a gamble you will almost always lose with modern high-speed signals.
So what is the best practice? If I absolutely have to transition layers and switch reference planes?
The honest answer, don't. Just try to route your critical high-speed signals without changing reference planes at all. But if you absolutely must, the only real solution is to place the planes as physically close together as possible to maximize that natural interplane capacitance. But really, the best practice is just to maintain a continuous reference.
Speaking of continuous references, there's one more way to absolutely ruin a plane: the Swiss cheese effect.
Oh yes, plane integrity. Sometimes you look at a board and the reference plane looks like it's been shot with a shotgun. Maybe there are too many vias clustered together and they merge into a slot. Or, even worse, someone has routed a signal trace through the reference plane itself.
They cut the floor in half.
Imagine you are walking down a hallway. That's your return current path. Suddenly, there is a giant hole in the floor. A canyon. You can't fly. What do?
I have to walk all the way around the hole to get to the other side.
You have to detour. This increases the path length. And in the world of physics, path length equals inductance.
And we know the return current wants to be directly underneath the signal to keep that loop small.
It's desperate to be underneath the signal. If you force it to detour around a cut or a slot in the plane, you are physically pulling the return current away from the signal. You are tearing that loop wide open.
And an open loop is basically a magnetic field generator.
It's an antenna. We're
Yeah.
broadcasting noise. So, rule number 1 of good layout: keep your planes solid. No splits, no cuts, no cheese graters.
This seems like a perfect moment to pivot to the why of all this. We keep throwing around the terms high frequency and low frequency, and I know there's a listener right now thinking, okay, this is great for you guys, but I'm designing a controller for a toaster oven. It runs at a few megahertz. It's basically DC. Does this really apply to me?
That's the digital myth.
Yeah.
And it is probably the single most dangerous mindset in modern electronics design.
Why? I mean, a few megahertz is slow, isn't it?
The clock speed is slow, but the physics doesn't care about how often you send a pulse. It cares about how fast that pulse transitions from logic 0 to logic 1.
The edge rate, the rise time.
Exactly. Think about a square wave. A perfect, ideal digital signal goes from 0 volts to 3.3 volts instantly. It's a vertical line on a graph.
Right.
But in the real world, to build that vertical line, you need math. Fourier analysis tells us that a square wave is actually made of a fundamental sine wave, say your 1 megahertz clock, plus infinite odd harmonics. So you got 3 megahertz, 5 megahertz, 7 megahertz, 9 megahertz, all stacked on top of each other.
So to make that corner sharp, you need a lot of high-frequency ingredients.
A ton of them. If your edge is very sharp, which all modern chips have, even the cheap microcontrollers in toasters, that transition contains energy well into the hundreds of megahertz or even gigahertz range.
So even if my clock is ticking just once a second, if that tick is sharp, it's a high-frequency event.
Precisely. And impedance behaves very, very differently at high frequencies.
Okay, let's break that down. Impedance is Zello dollars. It has a real part and an imaginary part.
The real part is resistance. That's just simple friction for electrons. The imaginary part is reactance, which is a combination of inductive and capacitive effects.
So how does the return current choose its path based on that?
At DC, or very low frequencies, current follows the path of least resistance. It's lazy. It wants the shortest, fattest copper path it can find. If you have a big plane, the current just spreads out like a spilled drink. Use the whole plane to get back home.
Okay, so at DC, it spreads out, but what about at high frequency?
At high frequency, which remember includes all modern digital signals, the inductance part of the impedance dominates. The current follows the path of least inductance.
And why inductance? Why does nature care about that?
Because nature hates stored energy. Inductance is directly related to the energy stored in the magnetic field loop. A large loop area stores a lot of energy. A small loop area stores very little. Nature always wants to minimize that energy state.
So the current tries to make the loop as small as physically possible.
Exactly. And the geometric way to make the loop smallest is for the return current to run directly underneath the signal trace. It bunches up. It constricts itself into this narrow band right below the trace.
That's fascinating. It's almost like the return current is actively shadowing the signal.
It's trying to. It really is. And our job as designers is to let it. If we put a cut in the plane, we prevent the current from taking that beautiful low inductance path. We force it to take a high inductance detour.
And high inductance means high voltage drops, ringing on the signal and radiated emissions.
You got it. So the takeaway is, assume every digital signal you have is high frequency. Assume the return current wants to hug the underside of its trace. And design your plane to allow that to happen.
This brings us to the final major topic, and it's a controversial one: separation. We always hear the rule, you have to separate analog and digital. Why do we do that?
Because digital is a bully.
A bully.
It is. Digital signals are aggressive. They have those fast, sharp edges we just talked about. They slam the voltage rails from high to low. Their fields are intense, and they're noisy. Analog signals, on the other hand, are very sensitive. They're the librarians. They're trying to measure these tiny, minute changes in voltage from a sensor.
So if the digital bully is shouting next to the analog librarian, you have a big problem.
That's crosstalk. It's unwanted coupling. If you run a high-speed digital trace right next to a sensitive analog sensor line, the magnetic fields from the digital trace will induce noise onto the analog line, and your sensor reading will be complete garbage.
So we separate them physically. Digital stuff on one side of the board, analog stuff on the other side. That makes perfect sense.
Yes, that is standard good practice. But here is the trap. And Dario Frisu highlights this as a critical warning because he sees it done wrong so often.
Okay, what's the trap?
The split plane trap. Some engineers think, okay, I need to separate analog and digital. So I will take my reference plane and I will literally cut it in half with a slot. I'll have a separate analog ground island and a separate digital ground island.
I feel like I've seen application notes from major chip manufacturers that actually suggest this.
They do, especially older ones.
Yeah.
But for modern complex boards, this is usually very bad practice.
Why, if separation is good, why is splitting the plane bad? It seems like the ultimate separation.
Because eventually those two worlds have to talk to each other. You will have a trace going from the digital side to the analog side, maybe an ADC converter line or a control signal.
Okay, so the signal wire crosses the gap, the moat.
But what about the return current? Remember our Grand Canyon analogy. If you cut the plane between them, you have completely broken the return path for that communication line. The signal goes across the gap, but the return current hits the moat. It can't jump.
So it has to go all the way around to wherever the two grounds are eventually connected.
Yes, usually way back at the power supply. You have just created a loop that spans the entire dimensions of your board. You have just built a massive unintentional loop antenna. You have absolutely destroyed your EMC performance in the name of separation.
That is deeply ironic. By trying to reduce noise, you ended up creating a giant radiator. So what is the correct approach then?
Keep the reference plane solid. Do not cut it. you achieve separation by placement.
Explain that. What's the difference?
You put all your digital components and traces on the left side of the board. You put all your analog components and traces on the right side of the board. Imagine an invisible line down the middle that no trace crosses, except for the necessary communication lines.
So the bullies stay in the gym and the librarians stay in the library, but they share the same solid floor underneath.
Exactly, a beautiful analogy. Because of the physics we discussed, the path of least inductance, the high-frequency digital return currents will stay strictly under the digital traces on their side. They won't wander over to the analog side unless you force them to by cutting the plane.
The physics naturally contains the noise for you.
Yes. If the plane is solid, the digital noise stays within the digital footprint. You get the separation you want without breaking the integrity of your return path.
So trust the physics. Don't try to outsmart it with a pair of scissors on your copper pour.
A solid plane is a designer's absolute best friend.
This has been
Wow.
illuminating. I feel like I need to go apologize to some of my old circuit boards for how I treated their return paths.
We all do.
I think I've been guilty of the Swiss cheese effect more than once.
It's a learning curve. We all start out with the water analogy, but once you put on the Maxwell goggles, you can't unsee the fields. You start looking at layouts completely differently.
So let's try and recap the journey we went on today. We started by realizing that the water in pipes model, it just leaks when it comes to EMC. It's all about fields, not just flow.
We visualize that invisible geometry, the electric and magnetic fields that are sandwiched between the trace and the reference plane.
We learned that the reference plane is the hero of the board. It contains the fields and provides the return path, and if you take it away or cut it up, you create a broadcasting antenna.
We discuss the loop. Current must return home, and it will take the path of least impedance. If you put a power plane in the way, you force it to use displacement current, which creates ground bounce and noise.
We covered transitions. When your signal switches layers, make sure its return current has a friend to go with it. Use a return via right next to your signal via to keep that loop tight. And don't rely on capacitors to do magic for you.
We debunked the digital myth. It's not about clock speed, it's about edge rate. Even your toaster controller is a high-frequency design, and high frequency always follows the path of least inductance.
And finally, the big warning. Separate your components by placement, but never ever split your reference plane. Keep the floor solid.
That is a very solid summary for a very complex topic.
Now, listener, if your brain is buzzing right now, good. That means new neural pathways are forming. But we have to be clear. We have only scratched the surface. This deep dive was based on just one segment of the knowledge available from Fresco Electronics.
Absolutely. We covered the what and some of the why, but the how, the actual implementation in Altium or Allegro or KiCad, that takes practice. If you want to actually master this, if you want to be the person in the design review who spots the failure before the board is even built, you need to go deeper.
So visit freesuelectronics.com. They have some incredible resources. And if you are serious about your career, you should join the Fresco Electronics Academy. That is where you go from learner to expert.
There is also the PCB hackers community. The link is in the description. It's a great place to find other engineers who are fighting the good fight against EMI every day.
So here's my final thought for you to chew on. We talked about Maxwell goggles, that ability to see the fields. The next time you open up your layout software and you're looking at that rat's nest of traces, just stop for a second. Close your eyes.
Don't see lines. See volumes of energy.
Can you visualize the black arrows and the blue circles? Can you see the return current flowing on the plane underneath your traces? And ask yourself this. Is my design a contained, orderly flow, or is it a leaking, chaotic storm?
Because the answer to that question decides whether you passed a test or whether you're back at the lab for a very expensive respin.
Thanks for listening to episode 4 of the EMI Control Podcast. We'll see you on the next deep dive.
Design with the fields in mind. Goodbye.